All right, so my name is Robin Gauthier. I'm a research scientist at the University of Illinois, 1 day a week, and then the rest of the time I lead the network perception startup, which is the company that develops and commercializes the NPView application, which is an application that started as a research project under the name of APT and then NetAPT some years ago. So the goal of this presentation today is to give everyone a bit of history and another view of what this tool can do and what are the next steps. So it all started a decade ago, actually, with a student, Senkalp Singh, who worked with Professor David Nicol and Professor Bill Sanders on his thesis project to try to automate the verification of safety policies implemented in firewalls. Then the project was funded by the TCG Center, and after Senkalp graduated, received a grant from the Department of Homeland Security for tech transfer, which means that the grant aimed at moving the project from a research product in the lab into a commercial product to have even more impact in the industry. And at that time, I joined the project, and we co-founded the network perception business with my colleagues Muna Bemba, Edmund Rogers, Professor David Nicol, and Professor Bill Sanders. And we moved to the UIUC Research Park incubator called Enterprise Works 2 years ago. When Senkalp started the project, it was called APT for Access Policy Tool. But then a few years later, the acronym APT became known for Advanced Persistent Threat. So we kind of had to move away from that name. So it got renamed to NetAPT. And then after the tech transfer and became commercialized, it got renamed into NPView. And so now that's the current name. So the goal, the motivation behind the first APT project was really to respond to a trend in the industry, which was to increase the connectivity with process control systems, process control networks. So decades ago, those analog systems were kind of disconnected and isolated from each other. And with the advance of communication technologies, they became increasingly connected to the corporate network and even sometimes to the internet. So the devices in charge of making sure that no harmful connection can go from unsecure zone into the very secure process control network zones are called firewalls. And those firewalls are configured to try to implement a security policy to make sure that the risks are limited in terms of intrusions. To give you an example of a policy, for this high-level view of an utility network, we could have rules such as all the outbound traffic should end in DMZ, or also called like demilitarized zones. And so we create DMZs between all those different zones, and the firewalls are configured that in a way that all this outbound traffic should end there, and using jumping stations to go to the next zone. That way you limit the direct connection between unsecured to secure zones. So the industry, in the electric industry world, this trend also are concerned some key stakeholder in terms of how to prevent that added connectivity from increasing the risk to the larger infrastructure. And so regulations were created, and those are called the NERC SIP standards. SIP stands for Critical Infrastructure Protection, and NERC stands for the North American Electric Reliability Corporation. So NERC is kind of the industry branch of this regulation consortium. And then on the government side, they have another thing called FERC. And so FERC approves the standards that the NERC is drafting with the help of the industry. FERC is also providing to Newark the authority to issue penalties and fines in case those standards are not respected. So the way it works today is that in the US, the country is divided into 8 NERC regions, and in each of those regions, utilities are being audited every few years by NERC auditors. And so those NERC auditors are reviewing config files from network devices, from firewalls, from routers. They're reviewing logs. They're asking questions to the utility engineers to make sure that all the standards are respected and that the utility is doing a good job in terms of protecting those critical networks from intrusions or from harmful connection. When a rule violation is discovered, fines can become pretty expensive. So what you see here on this slide is an example of a fine that was issued a few years ago, where a utility was received a penalty of $750,000 because they failed to identify some critical assets in the network. And those fines can go up to $1 million per day of violation, which means that if you have a violation discovered 30 days ago, then you can multiply 30 by 1 million a day, and that will give you the whole fine amount. So as you can imagine, utilities are very motivated to try to make sure that they comply with those regulations and try to make sure that they also are secure in terms of cyber intrusions. The problem is that those firewalls are configured using a set of rules and parameters that are stored in config files, and those files can be pretty complex and long to review. These slides just show you an example of a very small Cisco ASA config files in which the firewall has a definition for each of the network interfaces. So we have 3 of them defined on the left. Then definition of object groups, which are groups of IP addresses or groups of services. And then definitions of access rules, which are the rules that are allowing or denying traffic between interfaces and across networks. So if you imagine a utility network with 5 or 6 firewalls, and each of those firewalls have a config file like this, where they can reach thousands of lines with thousands of different access control lists, it can be very daunting for both the entities and auditors to try to make sense of all those rules and try to make sure that the network is well protected. If we look a bit more into the way a firewall is handling traffic, the key element is called the access control list, ACL. An ACL is a group of rules, and each rule will have a description of network traffic, often using the protocol, the source, and the destination information of that traffic, and then an action, either to accept the traffic or to deny, which means to block it, or to drop it, which means to block it and also to send an error message. And those rules are being treated by the firewall in a sequential order, which means that whenever a new network packet is received on one of the interfaces of the firewall will go through that table of rules and then try to match this new incoming packet with one of the traffic description. And if one match is detected, then the action from that match will be taken, and all the rules below that will be ignored for that specific packet. So it's important to understand that this ordering is critical, because if you add any permit at the top of your table, then you kind of compromise the rest of the rules inside your firewall. So not only you have the complexity of being able to make sense of each rule individually, but now you also have the complexity of taking into account the order of those rules and keeping like a mental model of which rule became first and how they are affecting the traffic when being received by the interface. And this problem becomes even more complex when you imagine that the policy can be distributed across multiple firewalls. So in a large utility, you can have hundreds of firewalls and routers, and so a given comprehensive safety policy can be spread across tens of those devices to make sure that the critical zones are protected. So the conclusion of that is that it's kind of impossible for human beings to do it manually. So that's where a tool like NPView came into place, where we can use algorithms and software to automatically read those tables, parse those config files, and make sense of it, and show the results visually to humans to make their job easier. So NPView, the former NetAPT, is a desktop application. It runs on all major OSs, on Windows, Mac, and Linux. It's designed to be pretty lightweight, so it's just a simple desktop app. It works offline, which means it doesn't connect to anything in the network. To run it, you simply select config files from network devices, so either from firewalls, routers, or switches. I have an example of 6 files on the left here. You put them into the tool, and the tool will go through a process that has 3 major steps. The first step is to parse each of the files. So the commands, the statements inside each of the config files will be understood, and the model will be built out of it. Then the second step will be to infer the topology of the network, which means that the way devices, hosts, and the gateways are connected with each other will be understood based on the relationship across IP addresses with the net mask and subnets. And then the third step will be to run what we call a path analysis, which is a way to compute the connectivity from every IP addresses in the network to every other IP address in the network. And that way we can see if the rules that I mentioned at the beginning, like the, ending all the outbound connection in the DMZs, for example, are respected by that network. And if there's no rule in the firewalls that are compromising that policy, or opening gaps, or opening adding risk to the network critical zones. And then the tool provides a way to export that data. So the tool is very visual. It tries to show a map, interactive map of the network, and then provides key features for users to export the results of the topology inference and the path analysis into actionable reports. So we have product reports, we have a rule audit table, a path analysis table, and then different ways to export the map. All right, so I have a few screenshots to show the tool, but let me switch to the tool itself and show you a demo instead. That may be easier to understand. All right, I hope you can still see my screen. Let me import the set of 6 Cisco ASA firewalls that I mentioned earlier. So when you select the files and put them into the tool, the parsing process, so this first box on my previous slide will get started. Each of the lines in the config will be parsed, and then the topology will be inferred. And that topology is this interactive map where you can see our 6 firewalls in orange, connected by networks, those little blue clouds. And then each network will host potential gateways or other network assets or workstations or servers. And for each of those, I can always double click on them, see their host name, their IP addresses, add a label, add a color, and understand how they connect to the rest of the network. So first value for NPView users is to get that visual view of the visual map of their network, and to understand how things are connected to each other. Users can automatically group the different zones that the firewalls are protecting, so that you can see where the remote access, internet access, corporate office, the SCADA network, the EMS, the energy management system, or the backup EMS are located in the network. And that zoning will help us when we do a path analysis to understand if there are paths that are violating the policy. In addition to parsing and doing this topo inference, the tool also will create a bunch of risk alerts to highlight potential misconfigurations or problems with the config files. So for example, if you have rules that are allowing traffic from any source towards any destination or just any services, then those risk alerts will flag those rules. And that way you can, when you do a rule audit job, you can review which rules can be risky, and understand the impact of that risk, and understand if you should revise the rule or if it's safe to keep it in the config like that. The rule audit table allows to do that. So it's a flat table of all the rules that were extracted from the devices. And if I go back to one of the devices to show you the native rule set, this is the native config file that was understood by the tool and then translated into that table. So for a user, it's easier to deal with that kind of Excel spreadsheet format on the left rather than having to understand the programmatic language of the raw config file on the right. And then users can review each rule one by one and approve them. So if there's no problem with the rule, they can just go through the list, add the justification, and audit them. Or if there's a problem, they can even flag the rules to review or to revise. All right, so this showed you the parsing stage and then the topology inference stage and the beginning of the audit stage. Now the third stage is the path analysis. So if I go to the path analysis tab and I start a full analysis, I will ask the model that the tool built in memory of the different firewalls connected to each other for the entire set of connections that this network allows. And what that means is that every time a firewall was imported into the tool knows how, depending on the vendor and the version of the firewall, they will handle this table of rules, and they will handle the order in which the rules are being presented. And based on that model understanding, then a simulation can be run to trace IP to IP connectivity across the entire network. And that's what this feature just provided. So when I send the request, the model ran the simulation, returns 1,641 individual paths. The map got highlighted to show me the source and the destinations of those paths. So destinations are in red, sources are in blue, and then hosts that are both source and destination will be colored with the two colors. On the left, I have the table that lists all the 1,641 paths, and I can click on any of those to highlight the path in the map. So that shows that this path goes from this outside network, crosses this corporate office firewall, it goes inside through an interface called outside, is allowed by a rule that allows traffic from 172.30 towards any, then it's allowed through a route, and then it goes out through an interface called marketing, and then reaches that final destination, the network, the host in red. So now that I have this feature, I can easily check what I mentioned at the beginning of the presentation, which was the high-level policy rules that govern my network and that protect my critical infrastructure. So, for example, if I have my primary EMS zone over there, I know that those are the most important assets. I can right-click on any of them and say, okay, show me the paths that are reaching this host. We see that we have result of 6 paths being returned. One of them is coming from a neighboring network, and it's the EMS database. Another one is coming from the corporate network zone. And then a third one is coming from a remote wide area network EMS host. So those two may be okay, but that last one, which is crossing 3 different firewalls before reaching that EMS zone, may not be a good one. Like that, I may not want someone from the remote access zone to be able to get access all the way towards my most critical asset in the energy management system. So if I do that, I can just find this path in my table, and then okay, that's a high-risk path, and now I can return that to my team, and then they can fix that path if needed. So to be able to get to that type of insight where you discover paths that are crossing multiple firewalls, multiple zones, requires this kind of software algorithmic understanding of each of the firewall rules to be able to be revealed visually to end users, and it's kind of difficult to do if you just have manual review of those config files. In addition to the direct connectivity, we can combine paths together by displaying what we call a stepping stone attack map. So if I select the same target and I say show stepping stone as a exposure map, another type of highlight will be revealed where this time in red I have hosts that can directly connect to this target. In orange will be host and network that could connect through a red jumping station, and then yellow will be the one that are 2 jumping stations away, like 2 stepping stones away. So these type of highlight reveal, like if I'm an attacker and I were to compromise this yellow host, I would have to first compromise the orange one and then the red one before being able to reach that target. So here we see the start of the buildup of what we call an attack graph, where we can combine paths together to understand how a security policy could lead to different levels of difficulties in terms of breaching zones and getting access to the most critical assets in the network. All right, let me go back to the slides. Root audit, path analysis, and then stepping stone, the thing that I just showed. So the tool, as I said at the beginning, so the tool is now commercialized by Network Perception. It's been there for 2 years. We still have research activity, R&D activity going on inside the company. Among the main work on which we're working now is the adding support for layer 2 connectivity, so being able to understand how switches and VLANs are augmenting or diminishing connectivity in the map I was showing. Also adding support for layer 7, so application layer firewalls such as Palo Alto firewalls. We're working on being able to do change tracking of full sets over time. So if one is using NPView to audit a network today, and then a month later you want to see what changed in the network, then you can import a new version of your config files, and then the tool will reveal some kind of a diff view of the topology to show what hosts or what network were added, removed, and also what paths were added and removed based on the recent changes. And lastly, we're working on being able to import additional network data into the map. So far we've been focusing on config files from firewalls and routers and switches, but we also want to be able to import network scan results from tools such as Nmap, where if you have a scanning campaign and a scan report with vulnerability information, to be able to import that report into NPView and augment the map with the host being discovered, as well as being able to import network traces from sniffers such as Wireshark or TCP dump, where you can extract the hosts that are communicating through the trace, augment the map inside NPView, and also validate the path analysis that NPView simulation engine provided with the actual paths that were recorded on the wire by your sniffing tool.
Robin, you have 5 minutes remaining.
All right, and I think I'm actually done. This is the list of publications and patents around that technology, if you want to learn more, and I'll be happy to answer any question.
Anyone have any questions?
I'll just toss a comment out there, which is for any of the CREDC-related researchers, we do have a installation of network perception for the testbed here at Illinois. If it's of use to your research, you can leverage it there, and Robin would be more than happy, I'm sure, to assist in determining how it can apply to your research if it's of interest.
Completely. Yep. Great point.
So I think if you recall last week that Salman Zanous
presented the CIPSA work, and a component of that uses some version of this tool, correct, Robin?
That's right.
Okay. So it is useful as a production thing, that utilities are using it to help them with audits, but it is also useful for research purposes.
Right.
So Sherry, we could wrap up. Let's thank the speaker.